In today's video, we will learn how to perform and interpret the independent t-test in SPSS. As a reminder from Monday's class, an independent t-test is used to compare means between two separate groups of people. We talked about how the independent t-test is similar to the two-way chi-square test in that we're comparing one group of people against the second group of people. However, the key difference is in a two-way chi-square test, we're comparing the percentages in one group against the percentages in another group. In other words, we're comparing the two groups in terms of how they score on some categorical variable. So one example of this would be if we wanted to compare Listerine users against non-Listerine users in terms of the percentage of each group that's been in a food fight before. Being in a food fight is a categorical variable. You either have or you haven't. So we could calculate the percentage of Listerine users who have been in a food fight and the percentage of non-Listerine users who have been in a food fight and use a two-way chi-square test to see if those two percentages are different. In an independent t-test, we're doing something similar, but the variable that we're comparing our two groups on is a continuous variable. So what we'll end up with is a mean for one group, a mean for the other group, and the results of the test will tell us if those two means are different from each other. So for example, if we had two samples, one of Listerine users and one of non-Listerine users, we could compare the mean income of Listerine users against the mean income of non-Listerine users, because income is a continuous variable. The results of the independent t-test would tell us if those two groups are different or equal in terms of how much money they make. For our first example today, we're going to draw upon the famous marshmallow study. You've all taken intro psych, so I'm guessing you've probably talked about the marshmallow study, at least to some extent. But in case you haven't, the marshmallow study is a famous study on the ability of children to delay gratification. Can children put off a short-term reward in order to gain a bigger long-term reward? Basically what they do is they put each child in a room and they leave them with one marshmallow, as you can see on the screen right now. And they tell the child, I'm going to leave the room. If you can wait until I get back and not eat this marshmallow, and I'll give you 2 marshmallows when I get back. So the child has to make a choice. I can either have 1 marshmallow now, or I can have 2 marshmallows later. As you can probably imagine, that's a tough thing for a young kid to do. If you've never seen it before, I definitely recommend this short YouTube video. It's only about 3 minutes long, and it shows some pretty adorable footage of these kids struggling to not eat the marshmallow. So if you'd like, I very much encourage you to pause right now, watch that YouTube video, and come back for the first example. So as you could see, this is a really tough thing for kids to do, right? Lamb and colleagues, a group of researchers from Germany, wanted to know if there are differences between different cultures in terms of children's ability to pass the marshmallow test. Specifically, they wanted to know if some kids were able to wait longer than others before eating the marshmallow. So what these researchers did is they administered the marshmallow test to 2 different groups of children. One group consisted of 125 children who were born and raised in Germany. The other group consisted of 76 children who were around the same age but grew up and lived in Cameroon and in a culture called the Enso culture. So these are going to be our 2 groups here. We have 125 German children in group 1, 76 Enso children in group 2. Our independent variable would be which culture, German or Cameroon, the children grew up in. The dependent variable in this study is going to be how long in minutes each child was able to wait before eating the marshmallow. So what we're going to end up with here are 2 means. On average, how long did German children wait before eating the marshmallow? On average, how long did Enso children wait before eating the marshmallow? We'll perform an independent t-test, and we will learn whether or not these two groups of children were different in terms of how long they waited. In other words, was one group able to wait significantly longer than the other group? Our null hypothesis says that there's no difference. So in this case, it would say that our two groups, German children and ENSO children, did not differ from each other in terms of how many minutes they were able to wait before eating the marshmallow. To test this hypothesis, we're going to use the data in the file marshmallow.sav. For each child, we know two things. We know whether they're from Cameroon or Germany, and we know how long in minutes they were able to wait before eating the marshmallow. To run our independent samples t-test, we're going to go to the menu that's indicated on the screen. Analyze, compare means, and right below one sample t-test, which we learned a few weeks ago, we have our independent samples t-test. When we click on independent samples t-test, as we're accustomed to seeing, we get a list of all of our variables in the left-hand side, and we have to pick our variables and move them to the appropriate boxes. Our test variable is going to be our dependent variable, which for an independent t-test is always going to be a continuous variable. It's the thing that we want to compare between the two groups. So in this case, it's how long in minutes each child was able to wait before eating the marshmallow. We would select that variable from the box on the left and use the top arrow button to move it to the test variables box on the right. Our grouping variable is our independent variable. In other words, it's the variable that tells us which of the two groups each person falls into. In this particular file, that variable is called culture, and each child is coded as having either come from Germany or Cameroon. Now, when you move the grouping variable over to its appropriate box, you'll notice that we see the name of the variable, which in this case is culture, and next to the name of the variable, we have a parentheses with two question marks in it. In order to run the test, we have to tell SPSS which numbers correspond to the two groups that we're trying to compare against each other. So to finish running this test, we may need to jump back to variable view and see exactly how this variable was coded. For example, were Germany and Cameroon coded as 0 and 1? Were they coded as 1 and 2? Which number corresponds to which group? If we were to do that in this case, we would see that Germany is coded as 1 and Cameroon is coded as 2. So any child that's from Cameroon has a 2 for the culture variable. Any child that's from Germany has a 1 for the culture variable. So in order to run this test and replace those question marks, we click the Define Groups button, and we're going to put in those two numbers in the two boxes corresponding to Group 1 and Group 2. I'll also remind you that the order doesn't matter. So we could put 1 in first and 2 second, or we could put 2 in first and 1 second. And we will get the same results. The only difference is whether t will be positive or negative, but it won't change our answer, it won't change our conclusion. However, if we accidentally put in 0 and 1 in these boxes, the test would not run properly and we would get an error message. So we would need to go back and check to make sure that we put the appropriate numbers in for the two groups that we want to compare. Once we do that and click OK, we get two tables in our output. The first table, called Group Statistics, gives us the sample size, the mean, and the standard deviation for both of our groups. So the 125 German children in our study were able to wait an average of 5.12 minutes before eating the marshmallow, and their standard deviation was 3.18. The 76 ENSO children who participated in our study waited an average of 7.8 minutes before eating the marshmallow, with a standard deviation of 3.9. Two things to note about this. First, if we were performing this test by hand, these are the 6 numbers that we would need to plug into our formula to calculate the t-statistic. Thankfully, because we have SPSS, we can ask SPSS to do it for us. Second, by looking at the means in this table, you might be tempted to conclude that Cameroonian children were able to wait significantly longer than German children, because by looking at the two means, those numbers look quite different. However, keep in mind that we don't know if this is a statistically significant difference until we look at the results of the t-test. So if we were to say now that these two groups were different, our conclusion would be premature. We have to look at the second table, the independent samples t-test table. Now, the first thing I want to warn you about with this table is there are two rows in it. There is one row that is labeled equal variances assumed, and there is a second row labeled equal variances not assumed. We are going to use the t-statistic and the degrees of freedom value in the top row of this table. You can ignore the ones that I've crossed out here on the bottom. So in this case, our t-statistic would round to negative 5.58, and our degrees of freedom is 199. Next, we need to look at our p-value. Now here's another thing that might be a bit tricky. There are two places in this table where we see sig, and we know that sig is our p-value. We're going to use the sig that's directly next to our degrees of freedom, the one that's highlighted in green. Do not use the sig that's next to t. This is something else. This is not our p-value. So in this case, our p-value is very, very small. It is less than 0.001. Remember that p can never equal 0, so if SPSS gives us 3 zeros, we know to write p is less than 0.001. So even though this table is very big and has a lot of information in it, there's really only 3 numbers that we are going to care about. The 2 that are highlighted in purple and the 1 that's highlighted in green. Since our p-value here is so small, it is well below 0.05, we can conclude that we have found a significant difference. We reject the null hypothesis, and our conclusion is that these two groups of children, German children and ENSO children, were not equal in terms of their ability to wait for the marshmallow. If we want to know which group of children were able to wait longer, we would look back at the means for each group in the previous table, and we would see that on average, the ENSO children were able to wait significantly longer before eating the marshmallow compared to the German children. So we have found a significant difference. It looks like children's performance on the marshmallow test does in fact differ between these two cultures. So if we want to write up our answer, it's going to look something like this. Remember to always begin by naming the test that you performed. An independent t-test showed that ENSO children waited longer before eating the marshmallow compared to German children. There in blue, we have the mean and standard deviation for each group separately, and at the end of the sentence, we have the results of our t-test. T with 199 degrees of freedom equals negative 5.58, and we have a very small p-value of less than 0.001. As a reminder for Monday's class, when we're running an independent t-test, the sign of t doesn't really matter, because the sign of t, whether it's positive or negative, is just a side effect of which group we chose to call group 1 and which group we chose to call group 2. So in this case, we could write negative 5.58 or we could write positive 5.58, and either would be correct. Here's a screenshot from the actual published study that this example is based on. It was published in a very well-known psychology journal called Child Development, and there's the title of the study. Now, here's a description of what the researchers did, right? Removing the wrapping from the marshmallow, placing it on a plate in front of the child. You can eat it now and you get only 1, or you can wait and you'll get 2. And they were left with a video camera that monitored what the child did while the adult was gone. Now, in this study, they actually measured two things. First, they measured, did the child eat the marshmallow, yes or no? And if they did eat the marshmallow, they also measured how long the child was able to wait before they ate the marshmallow, which is what we just looked at. Note that whether or not the child ate the marshmallow is a categorical variable. They either ate it or they didn't. So to test that variable, they used a two-way chi-square test. And what they found was that about 28% of German children succeeded in not eating the marshmallow and therefore got 2 marshmallows. However, nearly 70% of ENSO children succeeded in not eating the marshmallow. Up here in blue, you can see the results of their chi-square test with a very small p-value. Those percentages were significantly different. The ENSO children were significantly better at waiting to eat the marshmallow. Then they looked at what the researchers called delay times, meaning how long were the children able to wait before eating the marshmallow. And as we just saw, they found that the mean wait time for each group were significantly different from each other. And there's the results, the t-statistic, and again, a very small p-value. Our second example for today gets into a phenomenon called wishful seeing. It's the idea that people's desires and their physical states can actually influence, literally, how they see the world around them. So for example, in one famous study of wishful seeing, they gave students a backpack to carry, and it was either a light backpack or a heavy backpack. And they put them in front of a hill, and they asked them to estimate how tall the hill was. The people who were carrying the heavy backpack actually thought the hill was taller compared to people who were carrying the light backpack, presumably because the added weight of the backpack made the hill seem like it was really tall if they were to have to climb it. In this particular study, they brought students into the laboratory, and each student was asked to do one of two things. Some students were asked to drink a bunch of water, meaning they weren't thirsty at all. The other group was asked to eat a bunch of pretzels, which likely made them very thirsty. So the researchers created two groups of students, one group that was thirsty and one group that wasn't. Then they sat the students down at a table and placed a bottle of water on the other side of the table. And they asked the students to estimate how far away, in inches, the bottle of water was from them. The goal here was to see if the thirsty students and the non-thirsty students gave different estimates of how far away the water was. Maybe one group would see it as being closer, whereas the other group saw it as being farther away. You might remember this was one of the studies that was used on it as an example in your very first homework assignment. Our null hypothesis here, using the data file pretzels.sav, would be that there's no difference between these two groups. People who were thirsty, in other words, people who ate pretzels, and people who drank water, and therefore weren't thirsty, would not be different from each other in terms of how far away they thought the bottle of water was. Here again is how we would run our independent t-test. We would go to Analyze, Compare Means, and select the Independent Samples t-test option. Our dependent variable in this case is how far away they thought the bottle of water was. Our independent variable, which is called condition, is whether they drank water or ate pretzels. When we move condition over to the grouping variable box, we will again see those question marks that we talked about earlier. So we should go to variable view and see how that variable is coded. If we do that, we will see that students who drank water were given a 0 for the condition variable, and students who ate pretzels were given a 1 for the condition variable. So those are the two numbers we would put in the two empty boxes after clicking Define Groups. And again, the order doesn't matter here. We could put 0 and 1, or we could put 1 and 0, and the results of the test will be the same. However, if we were to accidentally put 1 and 2, we would get an error message. Here is the output for this independent t-test. The top table gives us the descriptive statistics for each of the two groups, the water group and the pretzels group. The bottom table gives us the actual results of the t-test. Before we go any further, I would encourage you to try answering each of these questions on your own. As shown in the top table, the people who were not thirsty, aka the people who drank water, they on average estimated that the bottle of water was about 28 inches away, 28.12 inches. The people who were thirsty, who had eaten pretzels, they estimated that the bottle of water was only about 25 inches away, 25.40 was their mean. In the bottom table, we see that our t-statistic was exactly 2.00, with 88 degrees of freedom, and our p-value was 0.048. Remember to use the p-value on the right, not the one on the left. So our p-value here would not be 0.397, it would be 0.048. Because 0.048 is less than 0.05, we can say that we have found evidence of a significant difference. The people who drank water estimated the bottle of water to be farther away compared to the people who ate pretzels. The thirsty people saw the water bottle. Here's how we would write up our results. An independent t-test revealed that thirsty participants estimated the water bottle to be closer than non-thirsty participants did. And it was about a 3-inch difference on average. Here's the results of our t-test. All of these numbers come from that second table on the previous slide. We also, in blue, have the means and standard deviations, which came from the first table on the previous slide. Again, this is based on a real study, and this is actually how the study turned out. Here's a description of the researcher's procedure, and here's how they explained their results. Notice they have their t-statistic with 88 degrees of freedom was equal to 2.00. Their p-value was equal to 0.05. And at the end, they included the means and standard deviations for each of the two groups, confirming that thirsty participants perceived the water bottle to be closer. Now you may be wondering why. Why should we care about this? What's the point of this study? The theory behind wishful seeing is that our brain actually plays tricks on us to try to get us to do things. Because these people were thirsty, the brain has a way of making the water appear like it's actually closer than it is. As a result, the water seems both closer and more obtainable, which should motivate the thirsty person to get the water, hence taking care of their thirst. Kind of neat how our brain knows what's best for us and plays tricks on us to get us to do the right thing. You're probably familiar with the phrase saving the best for last, but the third example we're going to look at today describes a phenomenon that these researchers called saving the last for best. Their theory is that people enjoy something more if they know that they're doing that thing for the last time. For example, imagine you find out that your favorite restaurant is closing and you go there for one final meal before it closes forever. They would hypothesize that you'll actually enjoy that meal even more than usual because you know it's your last one. The same thing could be said for movies or books or TV shows. Do people tend to enjoy the last book or the last movie simply because they know that it's going to be the last one? Take a second to think of other examples of this from your life. Some of you who are seniors or juniors will soon be experiencing many lasts. Your last party, your last time going out uptown, for example. Will you enjoy those experiences even more, knowing that it's the last time you'll do those things as a college student? To test this phenomenon, these researchers came up with a pretty clever, deceptive study. They recruited participants to do a chocolate taste test, and they had each participant eat a total of 5 Hershey Kisses. After eating each Hershey Kiss, they rated how much they liked it. Now, they mixed up the flavors. There were 5 different flavors of Hershey Kisses, and each participant got to eat the 5 Hershey Kisses in a random order. So there were 2 groups of people here. First, they were given a kiss, they ate it, and they were asked, how much did you enjoy eating that? And they rated it on a scale from 1 to 10. Then they were given 3 more Hershey Kisses. And the researchers said, here is your next chocolate. They ate it and rated it. Here is your next chocolate. They ate it and rated it. Here is your next chocolate. They ate it and rated it. Now for the 5th chocolate, here's where the 2 groups were different. One group was given the 5th chocolate, and they were told, here's your next chocolate. Meaning they didn't know that the 5th one would be their last one. The other group was given the 5th chocolate and told, here is your last chocolate. So they knew that this would be the last one. If these researchers' theory is correct, what we should see is that the group of people who knew that the 5th chocolate would be their last would rate the 5th chocolate as being better compared to people who didn't know that the 5th chocolate would be their last one. In the data file kisses.sav, for each person, we know which of the 2 groups they were in. Were they in the next condition, meaning they didn't know that the 5th chocolate would be the last one, or were they in the last condition, meaning they did know that the 5th chocolate would be the last one? We then, for each person, have their ratings of all 5 chocolates. The 1st, 2nd, 3rd, 4th, and 5th chocolates. Now, we wouldn't necessarily expect their ratings of the first 4 chocolates to be different, because up to that point, the 2 groups had been treated exactly the same. However, we would expect that their ratings of the 5th chocolate would be different, because one group knew that it was the last one, and the other group did not. Our null hypothesis, as always, says that there's no difference, that for that 5th chocolate, the people in the last group and the people in the next group would not be different. Here in one single table, I've condensed the results of 5 separate independent t-tests, one for each of the 5 chocolates. You'll notice that for the first chocolate, the 2 groups did not rate the chocolate differently. Same goes for the 2nd, 3rd, and 4th chocolates, all of which were rated as tasting equally good by the 2 groups. The 5th group, however, showed a significant difference with a p-value of 0.003. If we look at the means and standard deviations for each group's rating of the 5th chocolate, we see that the last condition had a significantly higher mean compared to the next condition. In other words, even though they were eating the same chocolate, the people who knew that it was their last one rated it as tasting better compared to people who didn't know that that was their last one. So if we were to write up the results just for that 5th chocolate, what we would say is that an independent t-test revealed that participants enjoyed that 5th chocolate more if they were told that it was the last one, rather than if they were told that it was the next one. And in fact, those are the actual results of the study. Participants in the last group rated the 5th chocolate as more enjoyable than participants in the next group. And they go on to say, as expected, ratings of the first 4 chocolates did not differ between the 2 groups. Here's a graph that shows for each of the 5 chocolates and both groups what the mean ratings of each chocolate were. Notice for the first 4 chocolates, the 2 bars were very close to each other, with the light gray bar representing the next group and the dark gray bar representing the last group. These first 4 chocolates were not rated as significantly different by the two groups. However, for that fifth chocolate, we see two very different bars. The last condition rated that fifth chocolate as being significantly more delicious compared to what the next condition did, even though the chocolate was the same. This is a real phenomenon. If you look, for example, at IMDb ratings of TV shows by episode, we see a pretty clear trend here, right? Here are the IMDb ratings for every episode of The Office. Each color represents a different season, and each dot represents an individual episode. For season 2, the highest rated episode was the last one. For season 3, the highest rated episode was the last one. For season 4, the highest rated episode was the last one. And if we look across the entire series, the highest rated episode overall was actually the series finale. This might provide some additional evidence that when something is coming to an end and people are watching it or reading it or eating it for the last time, their brain makes them enjoy it more. To conclude today's video, I will again refer you back to the class survey that you filled out at the beginning of the semester. Those data are published on our website, so you can play around with them and use them to practice these tests and study for exams. For the independent t-tests, I would encourage you to get together with a partner and come up with examples of hypotheses where you could compare the means between two different groups of people. For example, you could compare the mean number of shoes owned between people who live on campus and people who live off campus. What you may find is that there's no difference, or you may find that people who live on campus own fewer shoes than people who don't. You could also compare men and women, for example, in terms of how many days per week they exercise. Do men and women on average exercise the same number of days? Or does one sex exercise on average more than the other? Lastly, you could compare people who own a pet and people who don't own a pet in terms of how much they like chocolate. Chocolate is not good for dogs, for example, so maybe people who own pets like chocolate less. But again, you could test this out. My advice would be for you and a friend to get together, come up with a hypothesis, each of you test it independently and write up your answers, and then compare your answers against each other to see where you agree or disagree. If you both get it right, excellent job. If you find any differences, see where you went wrong and make sure you understand why you made those mistakes before you turn in the next homework.